welcome everybody. Today we're wrapping up our June talks they were all around runtimes and compute. So just thinking back a little bit, what we had David Calavera talking about the Rust runtime. Well, not the runtime, but Rust and how it works with Lambda. Richard Davison talked about LLRT runtime for Lambda. Luca Mezzalera talked about AWS Lambda performance tuning. So a lot of great talks. They're all recorded on the Believe in Serverless channel on YouTube. So make sure to follow us, Believe in Serverless or Believe in SLS and all the socials. So remember to follow us just to keep up to date. Just a little bit looking in the future. Next week, or well, tomorrow, I'll be doing a live stream where I'll be playing around with Amped. I've seen it a lot, but I haven't personally used it. So we'll see how that goes. Next week, on Tuesday, we'll have Danielle Heberling. She will be giving an introduction to compute on AWS. This is as part of our gun.io community collaboration. Make sure to tune in for that one. And then to kick off for July, our theme for July is going to be all about APIs. So we're going to start it off with Yan Kui in 2 weeks to talk all about production-ready WebSockets. So today we have Julian Wood, who is going to be talking to us about Lambda internals. Welcome, Julian. How are you doing?
Well, thank you, Andres. I am super good. So nice to be here. Believe in Serverless is cool. Finally, I get to get behind the velvet rope or the curtains or something and be part of a cool community.
Yeah, it's a great community. It's been growing so much. Started in January. We got close to 800 people, 800 members now. So
Fantastic.
Very excited. We've been able to get incredible talks every week. And this one, I'm super excited. I know I've seen some of this at reInvent. You do a lot of great talks around Lambda internals and under the hood. So excited for this one.
Cool.
So
thanks for inviting me. Yeah.
Happy to have you. So I'll let you introduce yourself and get on with the presentation.
Certainly. Well, hello everybody to, I suppose, people who are watching live as well. Super cool to be watching live. You can send me your questions and your comments. I will try to, spot them as I'm talking and see what goes on, or we'll, handle them in batches as we go. Andres, do you want to just stick up my intro slide and then am I sharing it? Yeah, cool. So yeah, I'm Julian. I'm a developer advocate within the sort of serverless thing at AWS. So yeah, love talking about serverless in general, and also talking about some of our various serverless products and features and things like that. I've been AWS just nearly 5 years. It'll be 5 years in September, which I think in dog years, that's many more years. It feels like it. But yeah, it's been an absolute blast. Big believer in the community. I love that Believe in Serverless exists and has so many passionate community members. I've been doing community things in IT for far longer than I've even been doing serverless, and I know we everything together with all the people. It's ultimately a people business, and so yeah, great to be talking to you today and be part of this community. So today I'm going to be talking about Lambda, and the sort of idea is, if you could close your eyes and, think of a future where your code just runs effortlessly in the cloud, just adapting to fluctuations in your demand without you having to do anything. No more server maintenance, no more sleepless nights, no more panicking about scalability. And this kind of future is not just a dream. It's actually what serverless compute is, and Lambda is a big part of that. And I'm not going to go quite into the basics of Lambda because I think people will know that as part of Believe in Serverless. But it's worth highlighting Lambda is a super cool service, and it's, we think, really the fastest way to build modern applications with the lowest cost of ownership. And the whole idea is to help teams build more and faster by doing everything that makes cloud development hard. And so we want to take sort of your distributed system challenges and then make them Lambda's problems to solve. And so this means as a development team, you can focus just on your code and then avoid as much of the maintenance costs and you sort of muck, we call it, or the drudgery of making the cloud software works. How cloud software works. And we use the experience at AWS, the compression algorithm for experience. And I think Lambda really is the ultimate of that, turning code into a well-architected service and trying to reduce the operational effort that you need, even though ops are still available. And of course, teams are doing everything with Lambda and serverless, from IT automation, data processing, huge amounts of data, building web fronts or web applications, building cool event-driven architectures, and of course, lots of machine learning, and obviously with Gen AI, which matches perfectly with using Lambda to be called something like Bedrock, and then on the other side using things like developer tools and Amazon Q, such kind of things, to actually help with developing your code or understanding your code or moving your code between different languages. So, part of the whole serverless thing, and particularly Lambda, is, we do a whole ton of innovation in all areas of the Lambda service to make the complex simple. We want to always give you more, while also crucially trying to keep it simple to use, so you can take advantage of all Lambda has to solve, many challenges sort of at many scale. And we always talk about the fundamentals of Lambda, and we focus on these things like availability, utilization, scale, and security and performance. And today I want to give you sort of some of our engineering stuff that we do under the hoods to make this all happen. And you may sort of hear that security is job zero at AWS, and that means that comes before everything else. It's not something that's reliant on anything else. Before we do even get to the numbers, security is important. And then after that, Lambda's going to focus on the operational excellence, because we are super keen on durability and availability. And we want to things like running your function in multiple AZs to ensure if there's any issue, we sort you out for that. And then we ensure these basics are covered before we even work on different kind of features. And with security being top priority, we've got this shared responsibility model, which has a separating line which defines what AWS is responsible, security in the cloud, security of the cloud. These are the infrastructure and software that runs the services, and your responsibility is for the security in the cloud, the security of your applications, and making sure your data is secure. But obviously, when building serverless applications with things like Lambda, AWS is able to take on even more of the security. So you have to worry less about things like OS patching and firewall configuration and maybe distributing certificates. And you get to focus more on your apps and data and let us work on the underlying platform. And so, an example of this, 2021, it's now a few years ago, but, it's a massively bad remote cold vulnerability in Apache's Log4j announced to the world. Just before Christmas, everybody is like panicking. This is absolutely crazy, trying to scramble to update Java across their environments. And but if you were using Lambda, we just handled most of it for you. Now, Lambda doesn't even actually include Log4j in its managed runtime or container images, so you were sort of already protected. But if it had been included, you would have been patched automatically. And then we also worked with a Java Corretto team, which Corretto is our Java implementation for AWS. And we built a mitigation that even if you had Log4j as part of your function code, at the service, we could just block the functionality and log that it had happened. And so Lambda protected you from a really serious vulnerability without you needing to do anything. And one of the major sort of technological foundations of Lambda is this open source Firecracker. Firecracker is certainly a cool name. And Firecracker is a technology that provides superb resource utilization to run your functions, and it's built with enhanced security and workload isolation. And it actually is all using traditional virtual machines, but with fast startup time. And so if you wanted to think about serverless functions with Lambda, the basics is how they work is there's an event source which is going to trigger a Lambda function, and this can be a change in data, something to do with a database update or something, or a file appearing in S3, maybe hitting an API endpoint. This could be via API gateway, it could be via an ALB application load balancer, could even be behind a function URL, and then resource state changes, reacting to kind of things with IT automation, and of course many messaging queues and streams with SQS and Kinesis and Kafka and things like that. And Lambda is an event-driven model. You've got the invocation methods and the invoke that was happening beforehand, and your code is then going to do something, and then the action that takes place after the code is finished running. And there's sort of 150 different services that can invoke a Lambda function, and in sort of 3 different ways that they do this. A synchronous invoke, which is often behind that kind of API, an asynchronous invoke where there's a queue in the middle, which Lambda is going to run on your behalf, and so we will just place a message to Lambda, and Lambda is going to then asynchronously run that function. And then a poll-based, which is the event source mapping. And this is when we pull data from, say, SQS or Kinesis or Kafka and run your function in that secure Firecracker micro VM. And in terms of packaging, your Lambda functions can be packaged as a zip archive and also as a containment image. So you've got some really good flexibility. So something that has come out recently, before I dive into some of the internals, is about Lambda function scaling. And Lambda function scaling is really cool because Lambda functions can scale up from 0 to a huge amount of function invocations. Lambda functions obviously run for up to 15 minutes and they're ephemeral. And so this is how the Lambda sort of lifecycle works, where a request comes in, request number 1 comes in, and we run your initialization phase, your cold start, and then we're going to run your invoke, and then we're going to keep that execution environment alive and available to run additional invokes like number 2 over here. If another invoke comes in parallel, well, we're going to scale up Lambda as well and run another version of your function, run the initialization code before, and then subsequent invokes are going to run without the initialization. And ultimately, after some period of time, we're going to shut down that execution environment because it's just going to keep that nice and tidy, and we don't have to. We can just tidy things up. And so recently, we actually updated the Lambda function scaling. And now Lambda functions can scale for 1,000 of those concurrent executions, as I showed previously, every single 10 seconds. And this is obviously great for applications which have various traffic patterns. And this scale just happens automatically without you having to do anything. So let me just show you the old model we had. So previously we had a burst rate. So we always used to talk about a Lambda burst rate, which was depending on the region. And so you had this initial burst in many regions, and there was sort of the stepping stone of original burst and then 500 per minute for each invocation. And so it meant you could go from 0 workers to 3,000 instantaneously and then step through. And what it would look like is at some point over 12 minutes, you would get to 10,000 sustained requests. And this is starting at 0, obviously. For general production workloads, you're typically not starting at 0 unless you're doing things like deploying a new function version. But so to get up to 10,000 concurrent requests, it would take 12 minutes. But now, with this new scaling behavior, the Lambda function scales with 1,000 requests every 10 seconds. And this is no longer also shared with other functions. So any other functions in an account that each have the same faster scaling behavior. And so what we're able to do is, like, in 90 seconds is get to that 10,000 concurrency rather than 12 minutes. And that's a dramatic reduction in scale. This really is the fastest way at AWS to get a whole bunch of compute power behind an application. And now it's even faster. And then another thing to understand while we're talking about Lambda is, memory is the power lever of the function. You can go, memory from 128 meg all the way up to 10 gig. And what that means is also there is then a corresponding proportional up to 6 virtual CPUs, which depends on how much memory you configure. And this means you can use Lambda for some pretty big memory and CPU intensive workloads. And also, because it's all done for 1 millisecond increments, it's a really efficient way to be able to have cost following your applications. So you know exactly per millisecond how much your applications are going to build. So there are 2 concurrency quotas to keep in mind. One is the account concurrency, and this is the amount of those parallel invocations that you can have within an account. And then that scale I've just been talking about, which is 1,000 instances every 10 seconds per function. And I see I've got a duplicate over here, so I'm going to flick over. I didn't hide the slides. But yeah. So now, obviously, to do all of this behind the scenes, Lambda has a whole number of control plane and data plane components, which we're going to talk about. Now, despite the rumors I hear, this isn't a talk about how we've sort of rebuilt Lambda over the past few years to sort of all run on Kubernetes or something cool like that. Absolutely nothing against Kubernetes, but Lambda doesn't run on a sort of traditional scalable container platform like that. Sort of just joking. We have to do our own thing because it is a crazy scale. And so we have the control plane, and these are where you interact with the Lambda service, you create, configure, and sort of manage your functions and upload your code. And then there are also a number of developer tools to integrate with Lambda, which cross then over to the data plane. And we've got things like console, CLI, SDK, all these kind of things. And then the data plane services are actually responsible for getting that event I spoke about to the Lambda service. And all invokes land up as a synchronous invoke, which you're going to show shortly. So we've also got a whole bunch of different services behind the scenes, and we're going to go into more depth later on how we've evolved some of these services and built new services to improve availability. So you can see the service here I'm talking about is the assignment service, and we're going to see how we coolly did some stuff with that. So let's have a look how how a synchronous invoke works. So requests to invoke a certain function arrive via an application load balancer. And this is going to distribute the invoke request to a fleet of hosts which run the stateless front-end invoke service. So Lambda is a multi-AZ service, so you don't have to worry about load balancing your functions across multiple AZs. Lambda just handles that for you. Now, I'm simplifying the diagram, or it gets a little crazy, but Lambda is built so all its components run transparently across multiple AZs. So the front-end invoke service is going to do some authentication and authorization of the request. And this is to ensure that Lambda is secure, as only authorized callers even get through Lambda's front door. And this service then loads the metadata associated with the request, and it's going to obviously need to cache as much information as it can to even get you the best performance. The front end then calls the counting service, and this checks whether any quota limits may need to be enforced based on the account burst or reserve concurrency. So it's not the burst anymore, but that scaling concurrency we spoke about before. And then the counting service itself is optimized for high throughput and sub 1.5 millisecond latency. As obviously it's called in each invocation, and it's critical to the invoke path, and so it's also made available across multiple AZs. Then the front end then talks to the assignment service, and this is a stateful service. We're going to certainly be talking about state today. So this is responsible for routing invoke requests to an available worker host. And the worker is actually the server in serverless. This is where the actual code runs. And it's responsible for creating a secure execution environment within that Firecracker micro VM I spoke about to download and run your code. And the worker is also responsible for managing the multiple runtimes and needs to set limits such as the memory based on your function config, and then also work out that proportional CPU. Now, here's also another component which does some coordination and manages background tasks. And this is the control plane service, which handles Lambda function creation and manages the lifecycle of the assignment service nodes, and makes sure that the front-end service is up to date with the assignment node to send an invoke request. So back onto the assignment service, this is, you can think of this as the coordinator. It's a distributor, it's an information retriever, and it's all about what state the execution environment currently is and where invokes should ultimately go. And it also keeps the front-end invoke surface up to date with which assignment service node to talk to. So for the first invoke of a function, a new execution environment needs to be created on a worker host. The assignment service talks to the placement service to create this execution environment with a time-based least. Now, placement actually uses some machine learning models to work out where best to place an execution environment. And it's going to take into its logic things like packing density for better fleet utilization, and also maintaining good performance and minimizing that cold path latency. It's obviously going to need to monitor the worker health and make sure it knows when a worker is unhealthy. And then we also need to make sure this runs as fast as possible to reduce latency for any cold start invokes. So once the execution environment is up and running, the assignment service gets your supplied IAM role so that the function runs with the privileges that you specifically define. It's then going to distribute that to the worker along with the environment variables. The execution environment then starts the language runtime, downloads the code, or runs a container image, and the function init process runs. And the assignment service then tells the front-end service, which sends the invoke payload to the execution environment. So hopefully we're not getting too lost in too many of the boxes over here. And then your function is going to run the handler and send its results back through the front-end service to the original caller for the synchronous invoke. The worker is also then going to tell the assignment service, yep, I finished my invoke, I'm ready for a subsequent warm invoke. So when a subsequent warm invoke comes in, the front end checks the quotas, and the counting service talks to the assignment service, which says, yes, remember, I just told you there's a warm and idle execution environment ready, waiting for you. And then he's going to send that invoke payload to the execution environment on the worker, and your function runs the handler, and then the worker tells the assignment service it's ready for another invoke, and the process starts again. Then when the lease of that execution environment is sort of nearing its end time, the assignment service marks it as not available for future invokes. And then there's a further process that's going to spin down and tidy up those execution environments. Also, if there are any errors within the init phase in the execution environment, the assignment is going to mark it as not available, and then it's going to be removed from the pool. And also, if something's happening with a worker and we need to remove it from the service, needs to be refreshed or has kind of any errors, we can gracefully drain it of execution environments by stopping any of the future invokes. So let's actually switch to talk about the asynchronous invokes, or what's also called event invokes. And you can see here that we have the event invoke front-end service. So the sync invoke had a front-end invoke service. Well, the event invoke service sits behind the same front-end load balancers as before, but the load balancers then see that this is an async event invoke, and so use this flow. And we actually separated these two services and building a separate data plane to ensure that an async invoke path was separate to the sync path. And this is to protect against if there was a large amount of event invokes, async invokes, we never wanted that to potentially cause any latency for the synchronous invoke path. Just another way that we can sort of improve availability and performance on your behalf. Again, it's all spread over multiple AZs. And so the front end then sends the invoke request to an internal SQS queue and then responds with an acknowledgement to the caller that it's going to invoke the function asynchronously. Now, it's not just one queue, it's many queues, and Lambda manages these queues, and you don't really need or have any visibility of them. And we run many queues and dynamically scale them up and down depending on the load and the function concurrency. And some other queues are shared, but we also send some events to dedicated queues to ensure Lambda can handle a huge number of async invokes with as little latency as possible. We then have a fleet of Polar instances, which we manage. And so an event invoke Polar reads the messages from this internal SQS queue to determine the account and the function and the payload, and then send the invoke request synchronously to the synchronous front-end invoke service and goes through that path I was talking before. So I did say briefly, all Lambda invokes ultimately land up as a synchronous invoke, which sort of makes sense. So also the sync front end is going to then return the function response to the Polar, which is then going to maybe delete a message from the queue if the response, if that has been successful. If the response is not successful, well, then the Polar is going to return the message to the queue, always going to delete messages that have been processed and leave the messages that have not been processed. And so, if you know about SQS, this is using the same visibility timeout as you use with your own SQS queues. And you can also configure event destinations for async invokes, and this provides callbacks after processing, whether the invokes are successful or they've failed after retries are exhausted. And there are some other control plane services involved. There's a queue manager, which looks after the queues, spinning them up and down and monitoring if they're getting any full. And then this is also going to work with what we call the leasing service. And this is going to manage which polars are processing which queues. And then it's going to detect if any polars fail, so their work can also be passed on to another polar. Now, when we built the Lambda async model, we also realized, well, hey, this idea could also be used for a number of other service integrations. So we built what is called an event source mapping. And this is a Lambda Polar resource that reads items from a source. Now, initially, this was only for Kinesis or DynamoDB, but we've expanded this to pull from your own SQS queues, many Kafka sources, including your own self-hosted Kafka. Yeah, that's not even an AWS service. And, Amazon MQ for Rabbit and ActiveMQ and a whole bunch of other services. And what the polars do, which is cool, is they pull messages from these sources. They can also optionally filter them, and they can then batch them up and send them to a Lambda function for processing. So this works as, you've got a producer application that is putting messages or records into the stream or the queue asynchronously. And then we run a number of slightly different polars, different tasks, or have different clients depending on the event source. And the polars are then going to read the messages from the stream or queue and then are optionally going to filter them. And this is a super useful functionality, and it's sort of built right into the system. It helps reduce traffic to your function. It's going to simplify the code and reduce the overall cost. And then it's going to batch the records together into a single payload and then send it to your function synchronously by the same sync front-end service I spoke about before. And then for queues, the Polar can then delete the message from the queue when your function successfully processes them. And then for Kinesis and Dynamo, you can also send information about the invoke to SQS or SNS. And the cool thing is we just manage these polars for you as part of the Lambda service. And this is really a huge benefit. You don't have to run and scale your own consumer EC2 instances or containers to poll for messages. And it's actually free. You don't even pay extra above your function invokes for the service, for the service, just part of the Lambda offering what it can do on your behalf. And there are also a bunch of other control plane services, the state manager, stream tracker. They're going to just handle looking after the whole service behind the scenes. And, having these polar fleets means we can support a number of event source features. We did the filtering and the batching, and we've got batch sizes and windows and reporting on partial batch failures, and, a whole bunch of functions and features which we continually adding to support these different polar functionality. So let's talk about Lambda and its resources. Now, you can provision Lambda functions up to 10 gig of storage per function instance, and this is a 20-time increase over the previous limit, which we had before, which was 512 meg. And the temporary storage is free up until the 512 meg limit, and you then charge for any storage you can provision after that for the duration of your function invocation. So yeah, sorry, I didn't properly switch that. You've got the Lambda 10 gig temp space, and you can have up to 10 gig, which you get charged for above 512 meg, but that's now 10 gig of available temp space. And then also you can have up to a 10 gig deployment package. And so this means, you can have huge Python modules, huge Java functions. You can do machine learning. You can, put a whole big bunch of stuff into your deployment package, and anything above, you can use anything above 512 limits. You can use, 256 gig limit. You need to use a container image to do that. Now, if we look at sort of Lambda storage in terms of the internal storage for temp and the memory storage and the deployment package size, you can see from 2019 what the size was. And in 2021, when we increased the memory and increased the deployment package, and then in 2022, we increased the temp space, you can see how dramatically bigger the Lambda storage has evolved over the years. And so, yeah, you can see just, this big size difference between that's happened over time. And so, in a way, you could sort of think of it as Lambda is, in fact, a storage service, because it is about storing things in RAM. It's also things about storing your code, and it's also about storing your application artifacts to get things around. And so there are actually a whole bunch of lessons from storage that we can take to build a well-architected storage service that are also equally applicable to when we're talking about Lambda. And so let's going to sort of start with lesson one, the sort of access patterns drive the storage layout. And, if you think about framing this topic, what state needs to be managed by the service in order to serve an invoke? Well, fundamentally, an invoke requires three things. It needs the invoke payload, and this is the JSON payload provided by the invoker or provided by the event source on every invoke. And secondly, it requires function code, and this is then provided by you as the developer when you are creating or updating the function. And then third, it requires a place to marry that invoke and the code, that micro virtual machine. And that's sort of two pieces of state and then one piece of state and compute that together form the necessary bits of information to serve an invoke. And then, as we spoke about the front-end invoke and the polars, these together serve to get the invoke input to the correct machine at the correct time. And so the next thing you obviously need is code. And when Lambda launched to deliver code to a machine to start up an execution environment, Lambda did the simple thing. We just downloaded the code from S3. So each execution environment started up with a Lambda service code, discovered what code payload backed the function, and then downloaded and unzipped the function code into the execution environment. And this allowed the VM to start the runtime and make the execution environment ready to go. And then it would accept the invoke and run. And this worked just fine and is still the architecture that backs the majority of functions today. But as our requirements changed, so did our architecture. And in 2020, we set out to build container packaging for support for Lambda. And this changed state management in a really big way, in that code payloads were now much larger. Zip payloads are limited to 250 meg. We realized the container images are often larger, and so we needed up to 10 gig max code size when packaging as a container image. And so the code delivery for architecture for Lambda made it such at the time to download and unpack function code scaled linearly with code size. And so, we thought this is really not acceptable, not possible for our new code payload requirements. And so this meant we actually had to rethink the mechanism. We couldn't just download the code from S3 to the VM because that would take far too much time. But, Lambda, along with the rest of the community, also sort of realized something, that many containerized workloads, the application is only going to read a subset of the entire container artifact. And this is a chart from a Harzer paper, which shows the disparity between total container image size, both compressed and uncompressed, and the data that's actually read into the container on execution. And while the mechanism Lambda uses ended up being different from that paper, we realized that if we could download and present it to the execution environment only the portions of the container image that are needed, well, then we could get the execution environment serving invokes more quickly and then get the code delivery time much quicker across many more requests. And so how to go from all at once loading of a container image to incremental loading? Well, first of all, we actually had to change the storage layout for Lambda container images. Now, this is what a simple Docker file may look like for a container image holding a Node.js function. And then when you build a container image from a Docker file, Docker produces a set of tar files called layers. And then Lambda is going to take these layers and it is going to flatten them into a file system. So once we have the flattened file system, we break its binary representation on disk into chunks. And a chunk is just a small piece of data that represents a logical range of the disk, and multiple chunks appended together may make up the entire logical disk and file system. Now, chunking is actually a really powerful construct because it lets us store content as a sum image quite in a granular way, and then access only the segments of the image that were required by the execution environment to serve and invoke. So here's an example here of a file system presented. When the execution environment starts, it knows nothing of the contents of the file system. And so the first access of the file system, maybe say to list the contents of root, results in an inode read. And then Lambda software is going to map that to a particular chunk in the image and fetch this chunk to serve the request. A subsequent read to a different node to open and say start the Java binary may fall to the same chunk, meaning no additional content needs to be loaded. So if there's any future kind of information, that must fall in a different chunk, and then chunks are loaded only as they are needed. And this means that, in total, Lambda delivers to the execution environment only the contents needed to serve the request the VM is actually making against the file system, and doesn't need to deliver content that is not needed. And so in this way, Lambda worked out lesson one. We took the understanding of customer access patterns, and specifically that container images are frequently and sparsely accessed, to drive the layout of the actual code storage in our data plane for efficiency and performance. So the second thing we were working on is sharing state without actually sharing state. And the other thing we realized about container images is they often share content with other images. And this is the simple reason that when people build with containers, you're obviously not starting from scratch. They're going to use base layers. This is base container layers, and a Lambda function may start with a base operating system layer, and then layer on top of that the Lambda worker Java runtime or Python runtime, for example, and then finally lay on top of that their function code. And then the Lambda data plane, understanding which data is shared and which data is unique, is helpful in optimizing code delivery. But it also turns out the DTube is difficult in this context for a few reasons. The first is that the storage layer is block instead of file-based. And so to allow two copies of the same file system state to share contents in the block level, they must be deterministically flattened into the file system and then deterministically lay out that file system on disk. But many file systems don't do that. And if you have some file systems, if you take the same set of layers multiple times and flatten them and then serialize them to disk, that means you actually get different representations on disks, which breaks the deduplication. So what we actually did is we solved this by doing some stuff in the ext4 file system to deterministically flatten and serialize when we were writing chunks to the disk. And the second reason dedupe is hard is all about key management. We need to encrypt things everywhere, and we need to have different encryption keys to protect the content of different customers, because customers can never be able to read their code, and AWS doesn't want to be able to read the code from different customers at the same time. And so, we needed a way that we can have secure content encrypted with the same data. Now, we could have done this with a shared key, but that's going to result in a single point of availability and then scaling this across multiple customers and resources. So we want the keys to be logically the same, but for the discovery of and the persistence of the shared key to be sort of pushed out closer to where the data itself is stored. And so we solved this problem. We turned it to this technology called convergent encryption. And when encrypted, then in a chunk of an image, we start out with a plain text chunk, which represents one segment of the flattened file system. And then we take the chunk and append some data that is deterministically generated by the Lambda service. And then we're going to compute a hash of that result. And then that hash result is then going to become our unique per chunk key. And then we use that key to encrypt the data, to create an encrypted chunk that not only contains the chunk data, but also contains the extra data as well. And so this is a really cool thing. And we can do this for each chunk in the file system, writing encrypted chunks to the chunk store and keeping the track of the keys for each one. And so this allows us to create a manifest containing the keys and the pointers. And then, we can also encrypt this with the customer-specific KMS key. And, there's just a whole bunch of great things about this encryption scheme. So, first of all, assuming we have the same data, we actually produce the same encrypted data from the same content every time. And this allows us to then securely dedupe content that should be deduplicated. And also critically, this allows us to actually dedupe while having each image creation processed independently without depending on a shared key. And then also, secondly, we can change the extra data to force two chunks to use a different encryption key, even if their contents are identical. And this actually helps us to ensure that content in a different AWS region does not share an encryption key, even if the content itself is the same. So yeah, a whole bunch of clever encryption stuff to make this work. And this allows us to improve the cache performance and economics to help overall performance of the system, all while minimizing the shared resources on which we take a dependency. And so, we've covered the invoke input delivery and the code payload delivery. And then the third part I mentioned is the state management, which I'm going to talk about. And this is the place where the input and the code meets the micro VM that runs on Firecracker. So, just quick look back of Lambda's history. Lambda operates a large fleet of EC2 hardware dedicated to running the millions of active functions in a region. And actually, at the launch of the service, which sounds crazy, Lambda provisioned T2 instances on that hardware and a dedicated T2 instance to each tenant to run more or one of that tenant's execution environments. And so, this did leverage the EC2 virtualization technology to isolate tenants from each other, different accounts and different functions from each other. And that was simple and secure. And so when a request came in, it would check for an existing execution environment. And if one did not exist, it would then initialize a whole new T2 instance with the information necessary to download the code. And at scale, this meant, many occupied instances in the fleet. And at any given moment in time, lots of instances in the process of being brought into service for a function or brought out of service to recycle for another function. But this also sort of highlights something that, while with code management, the goal was to scale up the state managed, with a VM fleet, we actually, the goal was to sort of scale down the state that managed. We wanted to provision as little needed compute, memory, and disk resources as possible for each micro VM. And, reducing these overheads is good for efficiency of the compute at rest and the efficiency which we can bring the VMs into and out of service. And so to do this led to the introduction of the Firecracker micro VMs into the Lambda architecture. And I mentioned before, it's a virtual machine manager that Lambda runs on bare metal work instances, and it uses Linux's KVM to manage hundreds or thousands of micro VMs on each worker. And this allows Lambda to benefit from a multi-tenant worker instance while using secure VM-level isolation between the execution environment and the customers. And then Firecracker is going to handle the I/O between the micro VM guest kernel and the underlying host kernel. And then within each micro VM is the execution environment the Lambda customer is used to, including the runtime, function code, and any configured extensions. So Firecracker also then allowed Lambda to both scale down and then right size while maintaining a secure VM boundary. So instead of, as before, allocating an entire T2 instance to each environment, we were able to deliver a smaller micro VM, potentially from an existing instance to each execution environment. This also means less overhead per VM, made our fleet way more efficient, and also makes the operations of standing up a new VM or recycling a discarded one way more efficient. And this move to Firecracker as a virtualization technology allowed us to do some other kind of things, sort of meeting the callers where they are. So what does that mean? Well, in our high-level architecture, we have our chunked encrypted images, and we have the micro VM that intends to make use of those images. But we also need to expose a usable container image or a file system into that micro VM. And in this regard, our job's a little harder with container images than it was for zip packaging. So just looking here at a single micro VM on a single worker host. So with zip packaging, since Lambda owns and manages the guest environment and runtime, we're able to deploy a small amount of code in the VM that knows what to do with the code payload to start the execution environment. But actually, if you think about it, with container packaging, the whole concept is that the entire guest environment is provided by you, the customer. So it actually doesn't leave anywhere in the guest to implement any image handling functionality, such as fetching from a chunk store and decryptions and that kind of thing. So with our EC2 virtualization stack, this wouldn't be possible. as running the guest as the only option. But running Firecracker on bare metal, we had space to then securely run service code, but actually outside of the customer virtual machine. And so we actually built a virtual file system driver that presents an ext4 file system from the worker into the virtual machine. So when the VM issues a request against the file system, they are handled by the Lambda code outside the VM. And then our file system implementation interprets the information to map the inode operations to access the correct chunk that needs to be accessed in the image. Of course, it needs to be secure, so it's going to interact with KMS to securely decrypt the manifest and that chunk, and then it's going to then serve the request to the file system and it's going to also consult various tiers of storage to be able to make this efficient and performant, from a host level cache to a larger in availability zone cache, and then also to the authoritative chunk store behind the scenes, which is S3. So all of this chunking, decryption, and cache tiering work is then entirely abstracted from the customer in your code behind a simple sort of file system interface. In other words, we actually met the caller where they were, abstracting away a lot of the storage complexity. And this sort of is part of this really cool storage journey, from the management of the invoke input to the management of the code and the container images. However, when we did this, we realized that all of the state management and all the work we did in the delivery made it that we could do some kind of stuff, but it also made us think about some sort of things like outlier latencies. And obviously, we're speaking about cold starts. Now, 99% of invokes to Lambda are served by an execution environment already in service. So cold starts are really, a small proportion of overall invokes. But, occasionally, if there's idleness or you need to scale up, an invoke does need to spin up a new execution environment before running the code. This is a cold start and impacts a function's latency. And so, spinning up a new execution environment means we need to launch a VM and download code, but also includes starting the runtime and initializing that code. And, the starting the runtime and initialization the code can, dominate the cold start time, especially for languages like Java, with a whole language virtual machine that needs to be spun up. And so this time and cost must be paid on every execution environment startup. And so, while cold starts may be rare, they can also be really impactful to the end user experience. And so, Lambda, we track a whole bunch of latencies at various percentiles, and outliers are rare, but we have outliers are rare, but they do have this sort of outsized impact on the customer experience. So outliers certainly matter to the service owners. So let's think about the initialization process, getting code into a running VM that's ready to serve and invoke. So what if we could use the storage lessons learned by Lambda to avoid this code to running a whole VM conversion process completely? So if we think about how to do that, what if instead of actually delivering code to the virtual machine, we were actually able to deliver a different artifact? Why don't we just deliver a whole running virtual machine to the individual host? And so that's actually what we're doing with Lambda Snapstart. And Lambda Snapstart automates the management of execution environment snapshots to significantly improve that outlier latency of Lambda functions. And it's initially available for the Corretto Java 11 runtime and is powered by the open source Firecracker, supporting VM snapshots and restore. So let's have a quick look how that works. So with Snapstart, the lifecycle of the execution environment is very different. When you update your function code or configuration and publish a new version, Lambda asynchronously creates an execution environment, downloads your code and config, and then initializes that execution environment, but just up to the point where it's ready to serve and invoke. And then Lambda is going to take a VM snapshot, it's then going to chunk it, encrypt it, and then store the manifest and the chunk contents. And then what's cool is on the invoke path, if a new execution environment is needed, all Lambda needs to do is restore a new micro VM from that persisted snapshot. And it can do this, at scale. And this is going to be a short restore phase, under a second, and the execution environment is then ready to serve traffic. And the result is to applications that sort of long tail latencies are really drastically reduced, and in many cases up to 90%. Now, you may note that one application in this sort of suite test that did not initially get much benefit from enabling Snapstart, but making a few minor code changes achieved the large speed up of the application samples. And a lot of this is moving some of the code from the invoke phase into the initialization phase. And so, maybe you need to do some code changes to benefit with this, but generally you just turn on Snapstart and it's going to be really cool and help you. And in a way, if you think about it, this improvement to cold start was actually made possible by turning what we think is a compute problem, turning code into running a VM, into actually a storage problem, delivering a virtual machine snapshot to the host. So, Lambda, we talked about Lambda as a storage service, is, we're going to use access patterns to influence how container images are laid out on disk. Shared state is important, how we're going to deduplicate that and make it available, scalable, and secure. And then also, how services are going to download that code to hide the complexities in running a storage architecture from the customer. So behind the scenes, we're talking about Java and snap start and some really cool functionality that we have as part of that. But we also have sort of state to deal with elsewhere in Lambda, and a little bit behind the scenes, but it's important to getting that event payload to the execution environment. So remember previously I said we had a worker manager, and this was this coordinator between the front-end invoke service and the worker. Well, it had a super important job to help the front-end get invokes to the execution environment and then manage the execution environment lifecycle. Well, previously we had an issue. It was one of the first parts of Lambda, getting a little bloated. And so each worker manager stored a list of the execution environments it was responsible for and on which hosts. So actually thinking of it in a state perspective, the state of an individual execution environment was only known to one worker manager instance, which stored it in memory. Obviously nice and fast, but you can imagine, it's not replicated. There's no redundancy. And so in this example, a worker manager in purple here, and if you can see the colors, manages a whole bunch of purple execution environments on a number of worker hosts. And we did have a control plane service to manage the worker managers. Now, if the worker manager fails, all those execution environments it was looking for are orphaned. They continue to handle their existing invokes, but for any new invokes, the front end has to ask other worker managers for an available execution environment. Now, other worker managers obviously don't know about the existing warm execution environments, so the placement service has to create new ones. And that's a bad customer experience of a cold start when there is actually a warm execution environment available, but it's orphaned. And this also means we need to have a bunch more spare capacity in the Lambda service to run these additional environments until we can reap the orphaned ones, which also impacts how efficiently we can run Lambda. And the issue gets even worse when you think about how Lambda distributes traffic across multiple AZs, particularly for smaller regions. And here we have an execution environment in AZ1 that is actually owned by a worker manager in AZ2. And if we have a zonal failure in AZ2, I mean, that's obviously extremely rare, but something we do need to plan for. All worker managers fail in AZ2, along with all execution environments on worker hosts. So that's a third of execution environment capacity in a region gone. Yet, as the execution environments in AZ1 and 3 that are registered to the worker managers in AZ2, also all of those execution environments, I mean, they are still up and running, and they're not impacted by the zonal issue, also become orphaned. So that works out to what? A third unavailable within each of the other availability AZs. And I think that's like a combined total of about 55% of execution environments capacity unavailable. So that's literally half of your execution environment capacity just not available. Now, of course, we have to hold spare capacity in Lambda to handle this sort of failure, but obviously it's really inefficient and also means we need to recreate a whole bunch of cold starts. And the placement service also needs to be able to handle this huge increase in additional requests. And so we decided that the worker manager needed a refresh, and so we built the assignment service. And instead of a single worker manager and a single AZ, we across multiple AZs, we built this assignment service, which is made up of 3 node partitions split across an AZ. So logically, a partition contains of a leader and 2 followers, each in different AZs. And we can run many partitions depending on the load. And then each assignment service node hosts multiple partitions. And then the assignment service, the actual members of this service then use an external journaling log service to replicate that execution environment data. And the leader writes to the journal, and then the followers read the log stream from the journal and to keep up to date with assignments. And this is a really efficient process. And so the partition members can also use the log journal approach to then elect the leader. So the front end talks to the leader communicates with the placement service to create new execution environments, and then keeps track of those assignments. If the leader fails, a follower can just very easily take over really quickly, and we don't lose any of the state. And this means far fewer cold starts and way less idle capacity needed, and less load on the placement service. And then when we do bring up a replacement follower, or we need to add service nodes to do this, it can just read from the log in the same time and just makes it really efficient. And we still need to have a control plane service, which is going to manage creating the partitions and make sure all the services can talk to each other. So, assignment service is fully resilient against all different kind of failures, from host network, even fully AZs, and using this partition leader approach. And means we can also slim down the service, making Lambda more efficient to run behind the hood. And actually, for those that are interesting, I know you've had some people talking about Rust before. This is actually written in Rust for performance and memory safety, and also the latency. And it actually tripled the amount of transactions per second that we can run on a host, and reducing the latency. So, I've spoken about a lot. This is all a part of the story on how we can build Lambda to really be the best place to run workloads in the cloud. And we want to handle as much of the hard distributed computing problems, especially with the state, so you can have the fastest way to build modern apps with the lowest total cost of ownership. We do have a site, serverlesslambda.com. This is a huge amount of resources for all things serverless on AWS, not just Lambda. Lots of learning guides and patterns and architecture patterns that you can do. But yeah, believe in serverless. So nice to see you. Thanks so much for inviting me. I'm happy to take any questions or comments that you may have. My contact details are over there, and happy to be part of the community and happy to talk about anything else you have. Anything that's coming up.
Hey, I was having some camera issue. I'm still mind blown, and it's like, what's happening?
I was thinking this is believe in serverless. These are people that believe in service. Serverless is, I could make this short and I could make it simple, but I'm thinking, you know what? I think people want to get the nitty gritty behind the scenes. Let's go straight in. So there's more I could have spoken about, so we can do another one and even do more.
Yeah, we can definitely get a follow up. It's incredible all that's happening under the hood, right? It's like I have a project. We have like 150, 180 Lambda functions. Just thinking all that's going on behind the scenes, for me to just be able to do response 200, right? From API gateway.
And even at the moment, I don't even know if this is public information, probably get into a little bit of trouble, but I'll say that like the whole sandbox way that we were running things before is literally being re-architected from the ground up. So there are trillions of invokes going on throughout a month at the Lambda servers. And we're literally building the whole sandbox functionality, which is going to allow us to be more efficient and give new functionality in the future. And that's all going to happen behind the scenes, and nobody's going to know. I love that whole part that we can it feels as though the speedboat is going, or no, maybe a car analogy. A Formula One car is driving super fast, and we can actually sort of change the tires while the car's still in motion. We don't even need to do a pit stop.
That's what's super cool. And I don't know if you saw a presentation that we had a couple of months ago with Liz Fong, and she was talking about Honeycomb. And on the fly, she was looking, I think they're testing a different kernel on my Lambda function, and because she was getting different logs. And it's like, wow.
Yeah.
So things are happening without
Liz and Honeycomb are, and we have loads of calls internally because they are pushing the boundaries of the system, and it's amazing to see how they've managed to evolve and do that. And these are big customers as well. And what's cool about working with customers like Honeycomb is they come back to us and go, no, we're having to do this ourselves. And we work with Honeycomb to take on, more of that operational stuff. So, customers like Honeycomb and, others, even, Vercel runs on Lambda. That's obviously massively huge. You can imagine what they're doing. Atlassian Forge are running customer things, many SaaS vendors. So, yeah, we work a lot with them to be able to, even do more on their behalf.
Yeah. And the best part is I don't have to do anything to get the benefits of all these things. And like you said, they're potentially changing the whole back end for it. And it's going to be faster and provide a better feature because it allows for more either extensibility or better performance with new technology. So that's pretty awesome.
Yeah. And it's one of the things I think is when you use Lambda at other serverless services, you're sort of investing in the future because nothing stands still. And for Lambda, we will run your code forever. But behind the scenes, things are going to get faster. There's going to be new functionality available, and that's the cool kind of thing that Lambda isn't a static service. Your code will run, but whatever investments you do in using Lambda are going to pay off in the future because there's just going to be more stuff to take advantage of, and a lot of that's just going to be it's going to be faster. It's going to be things get cheaper over time with better ways you can run things.
Yeah, it's sometimes it gets cheaper because it runs faster. And
Yeah, exactly.
So
Yeah. Well, there's an example, like EventBridge had reduced their latency, I think by sort of 90% early. I think it was earlier this year. And we had support calls from customers going, something's wrong, something's broken with EventBridge. Like my events are flowing much quicker. What have I done wrong? And we had to say, like, no, you haven't done anything wrong. We've actually improved EventBridge dramatically behind the scenes to be able to process those events much quicker. So you haven't done anything. Customers like, oh, okay, cool. I haven't done anything wrong. And you think, imagine getting support calls and being able to get that kind of message. You haven't done anything wrong. It's just got better without you doing anything.
Do you get calls like people that are consuming messages or something on an other architecture, and they're like, oh, now it's going too fast and we can't process them?
Yeah. Well, definitely that is the kind of case. And so, yeah, we've got to put in more controls and be able to, because Lambda doesn't work in a vacuum. It's got things that are coming in and it's writing to other kind of things. And so, even with the recent Lambda scaling, we've worked with a number of customers to say, okay, how does this impact the rest of your architecture? Because you could, flood a downstream API or some kind of thing. When Lambda had a built-in throttle that it couldn't scale as fast, you're like, oh, excellent. I'll just take advantage of Lambda, that slowness of Lambda, and we flip a switch and make it much faster. Like people are like, whoa, we're going to break something else.
Yeah. Let me see if there's any questions from the audience. I don't have anything. I do have a few questions. At the beginning, you were talking about the concurrency, that the default max concurrency is 1,000. I know I've bumped it up sometimes up to 5,000, 10,000. Is there a max? Is there a cap to how much if you have a good use case, right? Because I know they ask for architecture and stuff if you're going crazy, but is there a max concurrency at all?
We're improving that all the time. That often you can go just to the service quotas and you can request a limit increase. And that can be, I don't even know if there's a blocker on that, but I think I did an account and just set it to 15,000. In fact, I needed to do a Lambda scaling demo and just set it to 15,000. Now, maybe I'm internally and they, overly generous and maybe they trust me, which is a silly idea. But, the fact is we can do that kind of thing. And the quotas is also to protect you because, and one is from a performance perspective and one's also a cost perspective. If you've got Lambda functions, able to go, infinitely scale, cool, but you're going to pay for that. So, what that kind of do. I don't know if there is any maximum ceiling limit, but any kind of thing that is going to be, that kind of scale, the Lambda team's going to want to chat to you for two reasons: to understand your workloads, to see whether you can do things differently, because handling that kind of scale impacts, if you're writing to databases or you've got APIs, that's going to, so to make sure your whole architecture works as well. And then there may be optimizations that can be done, or things can be done asynchronously, or this kind of thing. Or they've got a valid use case. We can do this as well. So, and I know the Lambda team is very responsive and able to look at that. In fact, I love talking. Customers at big scale is an awesome thing to talk to see all the cool things people do.
Cool. Yeah, I think in my scenario, and I don't know if I operate in the Gov Cloud, right? So I'm assuming it's smaller fleets than US East 2 or, so they needed a better, or not a better use case. It was providing like the architecture and all to see if there was an improvement. And we usually need these for when you're running like a conversion, right? We're sending millions of records and stuff like that. But it's interesting to know if there is actually a cap. It seems like there isn't based on what I've seen.
There will be caps, but they're obviously, as you mentioned, for different regions and different kind of things, because they're just, they're still servers and serverless, and they, there's got to be some cap, and it's got to be, fair enough for all customers. But I'm unaware of any example where Lambda hasn't been able to scale, or there's been a huge amount of work going on in one particular region, and there were throttles because Lambda ran out of capacity. I've never heard of that happen. So
that's awesome to hear. In the async event invoke, right? There's an SQS in the middle, right? Just pretty sure I know the answer, but just want to make sure. Does that affect any of your SQS limits, right?
No, well, it's not your SQS so it's actually a Lambda service SQS. So we handle all of that. And we run many different queues, and we can put stuff on and off a queue in different places to do that. So that's and in fact that's a good thing to remember, that all Lambda functions run in the Lambda service VPC. So those sort of architectural things I highlighted run in the Lambda service VPC. And so when you invoke a function and you're running your code that's running in the Lambda service VPC, it's never running in your VPC. If you then connect a Lambda function to your VPC, all it means is that network routing goes via your VPC, but it's still your function code is going to run in the Lambda service VPC. But when it calls a database, calls an API, I don't know, does whatever, it's just going to route that sort of response, or not just the response of the function, but the actual work within the function through your VPC to somewhere else.
And I think it's Chris Munns that usually calls that out. It's you're connecting to the VPC. It's not running in the VPC if you add your own VPC. So yeah, definitely. Good call out there. And then last one is around snap start, right? That's only for Java. Yeah, will it be coming to other runtimes, or does it even make sense for other runtimes?
I mean, it definitely makes sense for other runtimes. I'll tell you the reason that it's only Java initially is actually for that for a security reason. That when you take a snapshot of a running virtual machine and then you restore it 10,000 times for 10,000 different concurrency, for example, you've got the same security seed that you've used to create that execution environment. And so if you were creating a cipher or you were doing something like that in that execution environment, if that is duplicated times 10,000, you've now got a potential security issue that can happen. Okay. And so Java has really advanced hooks. It's called crack, and restore, and the acronym's gone out of my head, but it's basically a mechanism built within Java to say, I can create a snapshot. When the JVM is restored from a snapshot, there's a Java thing that goes, let's recreate that seed, and you've already got your uniqueness again. And then Java libraries can go ahead and create a new secure SSH or whatever you need to do, but it's going to have a unique seed, and so that's going to be secure. And Lambda specifically decided we're not going to change the way that happens from a Lambda specific thing. We're going to rely on the Java community, which already has that, to do that. So it means this restore thing is a Java thing, not a Lambda thing, because we didn't want to write something that's specific to Java, specific to Lambda. If Java can do it, that'd be great. And so Java is way more advanced with that. Saying that, that doesn't mean other runtimes can't do that, and we are 100% looking at extending it to other runtimes as well. And so yeah, definitely, if you've got use cases for that as well, and I mean, I can think of examples for I mean, I'm not saying that this will be a next runtime, but an example of a huge big machine learning model in Python, for example, or .NET as well, that's also got potentially big cold starts. So yeah, I can't promise anything yet, but I know that we are looking at extending it to other runtimes.
Awesome. Cool. I don't have any other questions, none from the comments, but Julian, I really appreciate it. I'm going to have to rewatch this like 4 more times.
Sorry. I had to talk. Yeah, this is actually going to be a 2-hour chat. I'm going to have to talk much slowly, but I was like, we'll go for it.
Yeah, no, and I mean, there's a lot, right? There's a lot happening, and it's, again, for the serverless community to appreciate all the work that goes into this service, for us to just be able to focus on our business value, right? Writing the actual code, that's the ifs and fors. Basically, that's all we have to worry about at this point, and maybe fine-tuning the memory, the CPU, and the timeout, but that's it.
And there's always this balance between Lambda having more features and more things to expose, but also keeping it simple. But
yeah.
No, remember, I'm available. I'm active on social media or LinkedIn. If you have any questions or comments or ideas, or even suggestions to improve Lambda, please let me know. We work a lot with the product teams to evolve things as well as we can.
Awesome. Well, thanks a lot, Julian. Great talk. Happy to have you, and
cool.
We'll probably plan the part 2. But yeah,
definitely. Yeah, believe in serverless and keep the community strong. It's it's an awesome community. Love to be a part of it.
Thank you. Have a good one.
Cool. Cheers. Bye-bye.
Bye.